impairment. So I'll go and share my screen. Let's see here.
So the share button next to the leave button. So if you have the and there's multiple windows.
Yep. I just want to make sure I choose the right window to share my PowerPoint. But there. Can you see my PowerPoint slides?
Yes.
All right. Wonderful. All right. Just go into presentation mode. All right. So, yeah, I'll just go start off by giving a brief introduction about myself, just so there's a little bit of background and context about, why I'm here today and giving this talk on, digital voice, speech, and brain health. As was said in the introduction, I'm an assistant professor at Boston University School of Public Health and Department of Epidemiology. I've been here for about almost 3 years now, and before that, I did my postdoc fellowship also at Boston University, but in the School of Medicine at the Department of Anatomy and Neurobiology for a couple of years, and then before that, I was in Seattle at the University of Washington doing my PhD in epidemiology. As an epidemiologist, my research focus is really on prevention of Alzheimer's disease and related dementias, and so my current projects really focus mainly on modifiable lifestyle factors, looking across the life course on risk and resilience for ADRD. I also do some research projects related to traumatic brain injury and chronic traumatic encephalopathy. But what's most pertinent and relevant to this talk here today is some of my research around digital technologies to assess cognition. And this is a relatively newer area of research I've been involved in, especially since my time as a postdoctoral fellow at BU. So again, just a little more background about sort of how I got to studying this particular research topic. So during my PhD, I focused mainly on studying sensory impairments in older adults and the relationship with the development of dementia, mainly focusing on hearing and vision loss and impairment. When I came to Boston University for my postdoc, however, I joined the lab of Dr. Rhoda Oh and her Precision Brain Health Initiative, and also got connected with the Framingham Heart Study. And it was through some of being involved in some of Dr. O's research projects that I got to learn more about the digital data collection, specifically within the context of the Framingham Heart Study and during the neuropsychological exams, taking recordings of participants' voice and speech, as well as use of things like digital pens and things like that to record responses for written responses on these neuropsychological exams. And then I was fortunate enough to be awarded a SBIR STTR grant as one of the PIs in collaboration with a small business that was also interested in using machine learning approaches to predict early cognitive impairment, such as mild cognitive impairment, based on voice features collected in Framingham. So, I got some early hands-on work just through Dr. O's lab, and then as one of the PIs of this SBIR STTR grant, got to get really more involved in working with the data, learning more about the machine learning pipeline and ways to derive voice and speech features from voice recordings. And so I just want to acknowledge all those that have a lot more expertise and skills around this than I do. I mean, I think I've just been fortunate to be surrounded by a great team and people that are very much passionate about digital voice and in general digital data collection to enhance and improve brain health. And so these include, mentors and collaborators at Boston University, as well as at UMass Chan Medical School in Worcester, Massachusetts, and then some collaborators I worked with on the SBIR STTR grant, who were people with engineering backgrounds, who were audiologists, and provide a lot of expertise in terms of being able to make that project a success. All right, so I guess I'm just going to start off by talking a little bit about, why speech and voice and the capture of this data may be really actually a very powerful tool to enhance early detection of dementia. So as many of you may be aware, the need for early detection of dementia is gaining greater importance, especially now that we have, newly approved treatments for early AD. But as I just said, it's for early AD, so we need to basically be able to identify people in the early AD stages. And traditionally, this has been done through things like CSF markers or neuroimaging. And while these are great tools, the limitations with these tools include high cost and high subject burden. And this means that this can limit their applicability to other groups, particularly populations in lower resource settings, in effectively monitoring the dynamic progression of the disease. And therefore, there's an urgent need for an effective detection method that has a much broader and also much more inclusive reach for the early detection of AD and other dementias. Um, so speech is one of these avenues that I think has a lot of promise in terms of being able to fill that gap. Producing speech is a cognitively complex task that engages various cognitive domains. And it's also quite easy, relatively easy for audio data collection. And it highlights the potential cost effectiveness and non-invasiveness that using human speech-based features may offer to facilitate early identification of dementia, including MCI. Um, Studies have shown that language deficits can appear in the early stages or prodromal stages of dementia, often years before the clinical onset of dementia. But speech is not just about the word spoken or language. It's far richer in characterizing cognition than that. Audio recording can provide or yield a variety of attributes encompassing both acoustic and linguistic features. And both have their benefits. And later on, I'll talk a little bit more about some of the studies I've done with acoustic features of speech. So a lot of the information I'll be presenting here today is within the context of Framingham. I guess I'm biased because I've spent most of my time here at BU working with Framingham data. But yeah, and I'll stand on my soapbox here for a little bit and talk about the strengths of Framingham and why it's such a great study for looking at digital assessment, specifically digital voice and brain health and things like cognition. Um, so Framingham was very early to recognize voice as an alternative source of cognitively related information. Um, And since most people talk, digital voice analysis for cognition has the potential to overcome the long-standing education, cultural, and language biases of most cognitive assessment tools. And it's also known that there's quite a bit of heterogeneity in cognitive behaviors that makes it difficult to accurately detect fluctuations that can be representative of an early neurodegenerative disease process compared to those that are just kind of more normal fluctuations. And so the ubiquitous availability of recording devices can allow for much more continuous data collection and analysis of cognition that was cost and labor prohibitive in the past. And so Framingham being one of the earliest studies that has routinely collected this voice data and also combines it with a very rich set of cognitive and cognitive aging data. These are just some examples of papers that support the use of digital voice as an effective tool for identifying those who are cognitively impaired compared to those who are not. Um, oh, sorry, was there a question?
No, I
Uh,
think you're good.
okay, all right. Um, so just a little bit of the history of the voice recordings collected at Framingham. Um, Starting in 2005, Framingham began collecting digital voice recordings, and it's probably, it probably has the largest, recording or collection of longitudinal database, digital voice data that spans across probably around 2 decades, during which, there's been many cases of incident AD and dementia. And then, you can also combine that with the rich genotypic and phenotypic data that Framingham has collected over the years, and uh, you know, it's it's uh, it's quite amazing the amount of science that has been done, that is being done, and that can be done in the future with all this rich data. With all the data that's already been collected in Framingham now, with the digital data that's there. So uh, this is just a list of neuropsychological tests that are administered at the neuropsychological exams in Framingham. And these are the specific lists of tests that involve the use of a handheld voice recorder since 2005. Kind of moving along with, advancing technology. Now, since 2022, they've been using smartphones to also capture voice recording data on additional neuropsych tests administered in Framingham. And again, these are just some key studies, key publications that come out from Framingham using the digital voice data along with data science, AI approaches to creating prediction models for early detection of dementia. But it's not just in Framingham where, there's interest in science being done around digital voice. It's being increased. Obviously, there's increasing recognition for its importance, and so it's certainly spread around through the U.S. Within sort of the research communities. There are ADRCs, or Alzheimer's disease research centers, that are currently collecting digital voice recordings. So it's about 16 of the 37 ADRCs in the U.S. are collecting digital voice. They're part of the standard data collection as part of the ADRCs. There are 14 other ADRCs above and beyond the 16 that are currently collecting other forms of digital data. In addition to the ADRCs, there's the Alzheimer's Disease Neuroimaging Initiative, or ADNI, which comprises 60 sites across the US and Canada, and they've added digital voice recording to the protocol. And given the rich set of neuroimaging biomarker data, this is a great study, a great resource where they'll be able to validate digital voice biomarkers for AD against their collected imaging biomarkers. And then, and then as digital voice is being increasingly recognized and collected in studies and research centers, ultimately the importance and value of voice will come from its widespread implementation in the public. And smartphones may be an important sort of vehicle or marker to drive the collection of voice data. This is just a graph showing, the number of smartphone users in billions over the years since 2016. And this just kind of gives some indication of the potential how smartphones can be used to leverage voice collection, in a very widespread fashion. And then digital voice is already starting to be collected in clinical trials. This may facilitate faster recruitment, greater recruitment and enrollment in these clinical trials. In addition to clinical trials, industry, pharmaceutical companies are listening, no pun intended, but they're putting more investments and attention into development of speech analytics and voice collection tools as well. All right, so shifting gears a little bit. So, I think I've tried to provide sort of a broad overview of the importance of digital voice and its potential widespread use. What I want to do now is kind of go back down a little bit into a specific study that I worked on as part of the SBIR grant that I was involved with. And this was with, again, collaborators at BU, at UMass Chan Medical School, and collaborators at a small business to look at acoustic voice features that could be used to detect MCI in the Framingham Heart Study. Our focus here for acoustic features was mainly because we think that they provide accurate predictive ability of MCI, but the main advantage of acoustic features as opposed to linguistic features is greater privacy and security. Within Framingham, given the rich set of voice data, we were hoping that we could identify additional acoustic feature that would improve the predictive performance in terms of classifying those with MCI versus those without. Our study involved about 200 participants, 100 with MCI, and 100 participants that were cognitively normal. And then we included the voice recordings taken since 2005. Sorry, I'll go a little bit fast just to acknowledge the time because there's a few other things I do want to mention towards the end. I think one of the highlights of being part of this project was the development of this machine learning pipeline going from the raw voice recordings all the way to doing the supervised machine learning models to quantify the predictive ability of these selected acoustic features in classifying those with MCI and those without. So one of the first steps we had to take from the raw voice recordings was doing diarization, which is basically identifies and marks those that come from the participant versus those from the tester. This was important because, again, in Framingham, these voice recordings come from neuropsychological exams. So this is done in a standardized format, but there's typically two people in the room. One is the one who administers the test, and then one that is the participant. And so we just wanted to make sure that we were able to capture voice data that came from the participant rather than mixing it up with the tester. And then once we got the voice segments specific to the participant, we used some open source software, OpenSmile and Prot, to extract acoustic features from the voice recordings. And we were able to get over 6,000 features on acoustic properties from these audio data. Obviously, that's a lot. And so we first transformed the acoustic data into standardized scores, removed any outliers, and using t-tests, only selected features at a pre-specified level of significance to be included in the final machine learning model. For the machine learning model, for the classification model using supervised machine learning, we used a random forest model using a set of 29 features. We evaluated them based on tenfold cross-validation and calculated an AUC curve to quantify and model performance. In terms of the sample, we analyzed the average age was about 74 and 46% were female. And as I mentioned before, there were a total of 29 acoustic features that were selected for the final random forest model. I know it's a bit hard to see, but these were the list of 29 acoustic features that were significantly associated with cognitive status. This table also displays the importance of these scores for the classification of MCI with higher values indicating greater importance. And the most important acoustic feature for the MCI classification model was a number of filled pauses. And this was just the results from the AUC model. The optimal model was achieved when including these 29 acoustic features that were based on a z-score cutoff of 2. This was, again, for removing outliers and the p-value threshold of 0.002, which we got an AUC of 0.87. And so key takeaways from here is that acoustic-based features of human speech may offer easily collectible and accurate data modality for early ADRD detection. There's been other studies that have shown that frequency and duration of pauses increased in ADRD patients compared to those that were cognitively normal. So this, goes to support, in terms of identifying number of filled pauses as being the most important feature in our model. This was just the first study in future studies that we'd like to do with Framingham and other cohorts as well where data is available, but we'd like to replicate this in more diverse samples since Framingham tends to be more highly educated and predominantly white Caucasian, and also using biological markers of disease, to really look at the early biologic markers of AD, as well as incorporate more shared factors influencing speech and cognition, such as depression, which we couldn't include in this model because the data wasn't available at that time. So I guess I can finish here. So I know we're running up on close to time. So should I finish here, or would I have a little more time to do a few more slides? I want to also make sure I have time for a few questions if anyone has
So
any.
you have 30 more minutes. Or 33.
Oh, I see. I'm sorry.
Yeah.
I'm sorry.
No worries.
My time is wrong. Okay. All right. Wonderful. Thank you so much. All right. Okay. So then, yeah, I think we should be fine on time then. So that was just a little bit about the study that I was involved in, and hopefully there'll be more studies that I can use with the digital voice data in Framingham. But what I want to focus on next are just kind of think about next steps and some of the important considerations in terms of moving the idea of digital voice and brain health forward. So when I talked about digital voice in past presentations, past meetings, I think one of the most common issues or questions I face is around privacy and confidentiality. Just because voice may be traceable or identifiable to the participant, or there may be in the conversation certain things that may be identifiable or should not be shared. So I think privacy is one of those key concerns in terms of acceptability of voice as a data collection tool that is being addressed right now. And so I'm just going to share some of the things that collaborators have been doing at BU and other institutions to address this issue of privacy with voice data. So one of the approaches being taken right now is with pitch shifting and basically changing the pitch of the original voice recording so that it's harder to identify the speaker. And so these voice samples were taken from Dementia Bank, and we used pitch shifting to basically alter the pitch and essentially the tone of the speaker. And so I'm going to show an example of what that sounds like. So in this example here of a male speaking, you can hear the original voice sample, and then with changing levels of pitch shifting, you can get more privacy. So if we do a low privacy pitch shift, it sounds like this.
So can I say something? We can't hear these.
Oh, you can't hear. Oh, I'm sorry. Okay. All right. Well, the general idea here is that compared to the original voice recording, as you get increase in privacy by increasing the pitch shift, it becomes hard to recognize the original voice sample. And so there's been some preliminary studies looking at the use of voice obfuscation with pitch shifting to make sure that it achieves a good balance between making sure that it protects privacy, but also still maintains a good job of predictive ability. And as you see on the figures on the right, You see that as the pitch shifting increases, you increase privacy level, but you don't get too much of a decrease or sacrifice in the accuracy of these pitch shifted voice features in terms of their ability to differentiate cognitive status. And this is just an example of a workflow in terms of this privacy utility balancing concept, specifically with pitch shifting. And so you want to try and achieve a right balance between privacy, which is measured as equal error rate, and utility, in other words, classification accuracy of what you're trying to ultimately achieve in terms of differentiating those with cognitive impairment or dementia compared to those who are more cognitively intact or normal. There's also another approach called fictitious voice conversion, which also uses sort of this AI approach to taking original voice recording and either creating some kind of altered clone or something similar, but doesn't necessarily use the original voice or the speaker data to create this voice recording. And a lot of this work is also being done with collaborators at MIT as well. And then there's also something called contextual PII removal versus using large language models. And this is just basically, for example, you have someone who's a marathon runner who has lived in Boston and San Diego and completed their PhD at, for example, UC San Diego, and is fluent in English, Spanish, and French. The individual components may not be identifiable, but when you put them together, it could violate the 10,000 rule. And so using natural language processing or large language models, you can either do removal or pre-processing of PII. For example, you could remove the specifics of their PhD degree, their locations or fluency, but otherwise things that may not be as identifiable can still remain. I think we're also trying to explore whether NLPs and LLMs can help us to identify information beyond HIPAA that should be excluded as well from voice data. All right, and then the next thing I want to talk about is ultimately getting voice into being approved as a digital biomarker. This is, I guess, within the context of the FDA definition of a biomarker, which are characteristics that are objectively measured as indicators of health, disease, or response to an exposure intervention, including therapeutic interventions. And so digital biomarkers could be defined as a characteristic or set of characteristics collected from digital health technologies that is measured as an indicator of normal biological processes, pathogenic processes, or a response to an exposure or intervention, including therapeutic interventions. So, right now, a lot of the studies have looked at, whether digital voice, acoustic features, linguistic, paralinguistic features can differentiate, dementia from non-demented individuals or those with cognitive impairment versus cognitively normal. I think the next steps and some of the preliminary studies that are now going on, at least in Framingham, is using AD biomarkers taken from PET imaging, including amyloid and tau, and trying to validate those with voice features, whether they be linguistic or acoustic features, and those types of studies would help, I think, move the bar forward in terms of being able to ultimately validate voice or other digital markers as really a digital biomarker for Alzheimer's disease. And this is just a slide showing some examples of what digital biomarkers could look like based on the current definitions and categories of biomarkers. So we have different, categories of biomarkers, including diagnostic biomarkers, pharmacodynamic or response biomarkers, and monitoring biomarkers. And each of these biomarker categories serves a different purpose. And so these are just some ideas about, what types of digital biomarkers could fit within each of these existing biomarker categories in terms of, identification of a disease or a condition, or showing some kind of biologic response to an intervention or treatment, or just, in terms of monitoring, being able to assess disease status over time. And then I think the last thing I want to talk about is multimodal digital assessment. So I think, digital voice and voice recordings are a very promising avenue for enhancing early detection of dementia. But I think ultimately, voice will be a part of a much larger set of digital measures that are collected that can more accurately detect early cognitive impairment. This can include not only voice, but wearables from activity monitors that measure step counts, heart rates, intensities, digital measures of sleep, cognition, as well as retinal imaging, I think, are just some examples of how all these digital markers can be used to evaluate cognitive changes, cognitive status, and cognitive impairment on a much more accurate and scalable level than what's currently being done today. And so one of the big picture questions is, how do we get from collecting all this data from all these digital data modalities, and getting it so that we can process the data and analyze in such a way that it can come into an interpretable and usable model for clinicians and others interested in using digital assessments for brain health. The goal would be also to have, digital brain health as a standard of care where, again, it's not just voice, but it's a combination of voice with things like eye tracking, retinal imaging, physical activity monitors, sleep measures, things like digital pen, which are, again, being done currently in Framingham, and other smartphone applications to measure cognition. And you'd have this ecosystem of digital devices that that people and patients can wear, use in the real world, not just when they have to be in the clinic, but at their homes in their daily lives. This could provide much richer set of data over a much more continuous period of time than things that are done, for example, neuropsychological evaluations that are done on on 6-month basis or even longer. This could be something that is much more scalable and applicable to many more people, not just across different resource settings and populations. And I think the idea with these digital assessments ultimately is that digital is the new blood. To facilitate precision brain health, it requires precision recruitment, precision monitoring, precision detection, and precision treatment. And with these digital assessments and these digital tools, it'll facilitate that ability to enhance precision brain health, along with data and computing analytic tools to analyze all that data. So the analogy between digital and blood is that we've collected blood for a long time, kind of to measure what is known and to store for later use. Genetics and genomics are an example of that precision-based medicine that has been enabled by the availability of stored blood samples for the latest and greatest in blood-based biomarkers across multiple disease states. And so digital data streams in the raw native format are not dissimilar to a raw blood sample. You can measure step counts, heart rates, sleep patterns, track through validated algorithms that analyze the raw digital data streams and convert them into clinically meaningful measures. And then also, like blood, digital data can be stored and reused whenever a new algorithm is developed for a wide range of context of use. So, it's not like a limited quantity. if you use it, it's not like that amount of blood is no longer usable. It's still there. And so, unlike blood, digital data is a non-diluting resource. It can be reanalyzed repeatedly and frequently without losing its value. And old measures based on quickly outdated algorithms can be brought up to contemporary levels in real time at low cost. So, this is not just something that matters and is applicable for today, but this process, the data, can still be very valuable in years in the future when algorithms, when tools become more advanced. That same set of data can be leveraged and used for those purposes later on. And I think that's what makes digital data also a very valuable resource to collect. Um, And so, yeah, I think just in terms of a concluding remark, I think because of these infinite possibilities with digital data now and in the future, digital is the new blood, and it's very exciting to see how voice and other digital data streams that are being collected right now can be used to enhance detection of cognitive impairment and ultimately promote better brain health. Throughout the life course and across different populations, across resource settings, so that it's not just a tool that can be used for a select few, but can be used for everyone to ultimately enhance their brain health over their lifetimes. Um, so with that, that's it in terms of my slides. Yeah, I have some time for questions now. I guess, yeah, I thought I had less time. I'm so sorry about that. And so I kind of sped through the slides on my study. So if you want to go back to that, if you have any questions there, I'm happy to talk more about that study or anything else that I was presenting here today. I'd be happy to talk about with the audience today. So thank you so much for your attention and time today.
Dr. Huang, thanks for the presentation. Quick question, like you showed the random forest classification performance. Can you go back to that slide? I
Yes,
didn't
sure.
look carefully.
I'm sorry, I'm sharing the wrong. Are you looking at just
Right, just
this
this
part?
early, yeah. What's the sample size here?
It's 200. So 200 in the sample, 100 with MCI, and 100 that are cognitively normal.
Also just binary classification.
Yes, yes, yeah.
And you have
Yeah,
a AUC of 87 on the
yes,
next slide.
yep.
I see, I see. Well, why using random forest here? Because you use deep learning to extract feature anyway, and then the last layer becomes random forest. Why don't you directly use CNN or STM kind of model?
I think we used random forest because of its, I mean, I think we considered different models, but I think we settled on random forest uh, partially because that was a
The best
model that
performing.
the analysts were more familiar with
Okay,
than like
okay,
CNNs, and also the ability to generate importance features of each feature in terms of their contributions to the model performance.
okay, I see.
But yeah, I mean, I think CNNs, deep learning, those are all approaches that I think are right now also being used in Framingham as well with this data.
Yeah, because there's assumption, right? Like random forest is just take all the features in combination and look at their joint interaction. And then if you use CN or STM kind of approach, autoregressive, so there's moving forward, so you can look at dependencies. A different assumption. Maybe with this small sample size, I think random forest perform well. But if you have a bigger sample size, those deep learning methods will be more robust typically.
I see, I see. That's helpful to know then. Yeah, I think as we continue to collect more digital data, more digital voice data, I think yeah, we'll look into using those approaches as well for future projects.
Thank you. So are you taking both the voice feature and then the language into separate channels, or you combine them?
So here we only extracted acoustic features from the voice recordings.
Right.
We didn't use any language or linguistic. We didn't extract or identify any linguistic
Say
features.
people repeats words or long delay between response. Those are critical features too, right?
Yes, I mean I'm sure those are very important features as well,
Oh.
but we only focused on acoustic features for this
Get it.
project. Yeah.
Get it. Is this data accessible?
I guess the short answer to a long answer is it is available, but because this is within the Framingham
Right.
ecosystem, there typically needs to be like a data transfer agreement.
Yeah.
So it's not, unfortunately, like even as investigators with using this data, it's not within our control to just give it out to other researchers. There needs to be like a formal data transfer agreement process. But if you're interested, certainly, I'd be happy to talk more about that too.
Okay, I understand. Thank you. Yeah.
Yep.
There's also AD&I, as you mentioned, right, Philip, that I mean, all this voice recordings are going through the ADRCs, I imagine.
Yes.
So as there's more interest in this area, I imagine that besides Framingham, now you have other sources, as you mentioned,
Yeah.
of recordings.
Yeah. So, yeah, the ADRCs, not all of them, but some of them are currently doing digital voice recordings, and it's being part of the UDS. So I would imagine that, these voice recordings would be publicly freely available for researchers, once they're posted on the NAC database.
Right.
Hi, Dr. Hwang. Thank you so much for your presentation. I had a quick question.
Mhm.
The model, the audio recordings which had MCI, were they very obvious that a human was also able to identify that, yes, this is an MCI? Or did you see the model being able to identify subclinical forms of MCI, which maybe the model predicted, and then if a human kind of read through it and heard it again, were these do you expect such things to happen in the future?
So you're talking about like in terms of getting the voice recordings, were we able to identify like sort of overt case of MCI just based on like listening to the voice recordings?
Yeah. Like the experts, if they looked at it, was it
I
very
see.
Yeah.
I see. Yeah, that's a great question. So in this project, we didn't actually have like an external person actually listen to the voice recordings and classify if they thought someone had MCI or not. So we don't have that information. Um, in this case, MCI was classified and adjudicated separately within Framingham as part of like a dementia review panel. So all participants who are flagged for potential cognitive impairment based on their NP test scores are then sent to a dementia review panel, and then they decide whether this person has MCI or dementia. So that's how we classified individuals with MCI versus not having MCI, was based on the determination made at these consensus meetings. So yeah, I guess to answer your question, I mean, yeah, we didn't have anyone actually listen to voice recordings, assess whether they think they have MCI or not, and then compare that to, what the model found. That would be an interesting thing to do, but we didn't do that here in this project.
Thank you.
I think I have like a probably related question. So are you aware of any modeling in aphasias? Like, it happens, like, so it's like sort of a distorted kind of acoustic or speech. Are you aware of like methods in those aphasia?
Yeah, that's a great question. I don't. Yeah, I haven't done really any studies around aphasia and voice so far. And I'm not sure whether that data would exist in Framingham. I'm not 100% sure, but I'm not familiar with any data collected on aphasia in Framingham. But obviously, that would be another important area of research to do concerning voice changes and fluctuations due to aphasia.
Yeah, I think you mentioned, I guess Framingham has been collecting recordings for, did you say since 2005?
Yes, since 2005, so 20
Yes.
years now.
It does really put you in a unique position in Boston to, study the predictive marker capability. When I think about, people who are being followed for decades.
Right, right.
And, we're looking obviously at these concepts that people develop symptoms that are maybe non-specific in some ways, or but end up actually being the first manifestations of a neurodegenerative process.
Yeah.
And so I just think that does have some unique advantages in terms of Framingham versus, let's say, ADRC.
Right. Yeah, I mean, Framingham enrolls participants across the adult life course, as early as 20s, 30s, and 60s and on. But it's really the value of getting this voice data early on, like when they're in midlife or something, being able to follow them up for 20, 30 years as they get into older age, and then starting to, potentially see changes in cognition and being able to correlate the longitudinal measures of voice with their longitudinal measures of cognition over time.
Yeah, because my hope is that you'd be able to get to a stage before MCI, that in terms of the prediction, where it seems like our MCI to me is already a bit late. And, we need to have classification systems that go even before that. And,
Right.
and we have biomarker classification systems now.
Right.
But, even from a clinical perspective, and, voice may be one of those places.
Yeah. Yep. Yeah. So I think, Framingham is just starting to collect some more of the biomarker data. But yeah, I think going as early as you can and trying to characterize some of the changes that predict, those that go on to develop cognitive impairment, dementia would be really exciting to see.
Well, thanks so much, Philip.
Yeah, you're welcome. You're welcome. Again, it was wonderful to present here. Hopefully it was interesting and informative. Yeah, if anyone's interested in learning more about, at least the voice data at Framingham, feel free to reach out. I'd be happy to chat and share more about, this data.
Hi.
Hello.
Yeah, I just wanted to ask you about the acoustic features that you extracted for your model. Can
Yes.
you please explain the process by which you extracted the features and you selected the most relevant one?
Sure. So yeah, this is the workflow about how we started from the raw voice recordings, did diarization to make sure we isolate the voice data specific to the participant. And then to your question, how we got the acoustic features. So we used a couple of open source software called OpenSmile and Prot that able to extract the acoustic features from voice recordings. And in this case, we got from these voice recordings over 6,000 acoustic features. So that's way too many to do an analysis on. So we were able to select based on these 6,000 a total of 29 acoustic features that were included into the final classification model. And the way we select the process for selecting the final 29 acoustic features from this initial set of over 6,000 is that first we transform the features into standardized scores, z-score specifically. We remove the outliers, so those that were either greater than or greater than two z-scores or lower than two z-scores. And then we did a t-test to look at the relationship between each feature in comparing those with MCI and those with those who are cognitively normal. we set a level of significance of 0.002, and those features that had a p-value of less than 0.002 were ultimately selected to be in the final classification model.
Okay, okay. So are your results are published? Are they available?
Yes. This is the reference to the paper that involved this identification of these acoustic features for classification of MCI. So it was published just last year, I believe, in JMR Aging.
Okay, okay. Thank you so
Yes.
much.
Yep, you're welcome.
Okay. I think if there's no other questions, yeah, thanks again, really, for the great presentation. We look forward to, to having you probably one more time. So, yeah, and yeah, it was great. Thanks.
Yeah.
Thank you.
Yeah, definitely. Thank you so much, Fadi, for again hosting me here today. Yeah, I hope that this was helpful and interesting. And yeah, I'd love to come back and talk more about digital voice or other digital data for brain health. But yeah, maybe until then, I hope everyone does well and enjoys the rest of their afternoon.
Perfect. Thank you so much. Thanks.
All right. Thank you.
Thank you,
Take care,
everybody.
everyone. Bye-bye.
Bye-bye.
Thank you.